Okay, as I've said, probably privately but not publicly, the homework assignment that was supposed to be due today will not be due today because we haven't covered Gauss's law yet. So I'm going to cover Gauss's law, and hopefully I will have some time to look at the problems as well. So Gauss's law is a law that actually fits something we've already learned. We learned that electric field lines come out of positive charge and go into negative charge. And the more positive charge you have, the more lines are going to come out, because you can have a stronger electric field. And so we've learned those rules, and Gauss's law is a calculation that allows you to find the electric field strength based on the electric field lines. So what Gauss said was, I can take a shape. Now this is a shape that I'm using in my brain for calculational purposes. It's not an actual physical shape. And if I can calculate how much electric flux is coming through the surface, I can tell you exactly how much charge is enclosed. Now, of course, electric flux is a term we have to define. The electric flux is the electric field through the surface, and it's calculated by taking the dot product between the electric field strength, well, the electric field vector, and the surface. So electric field flux, we use the Greek letter phi. I'm going to put a subscript of E because later on we'll talk about magnetic flux. In general physics textbooks, they write it as electric field dotted to area. Now, you see I left some space there so I can correct it. What does it mean if it's a dot product? 3 of you are in calculus class and had a test covering those yesterday. I know you probably didn't want to be reminded. What does it mean if it's a dot product?
You multiply the first two posts. Like I'm going to break it up so it's easy, but like you have like E1 and E2 and A1 and A2. You have E1 times A1 plus E2 times A2.
Okay, now to make sure it's clear for everyone, E1 is the component in, let's say, the X direction, and E2 is the component in the Y direction. You're multiplying the parallel parts. So dot product is multiplying the parallel parts. So it's measuring how much electric field goes through the surface. But that presupposes something else. What direction is the area of the surface? Like this tabletop, what direction is this tabletop? Okay, normal to the surface. That's how we define the direction for the area, the normal to the surface. So this tabletop's direction is straight up, whereas this drawer, the direction of this thing here, is straight horizontal. So we're doing the dot product multiplying the parallel parts of the electric field times area. Now that's all fine and good, except what if my electric field is changing or my area is not a flat area? Well, then we have to add up all the pieces. And so sometimes you'll see this written like this, a sum of all the electric fields dotted to the areas for each surface. So if you have a cube, the cube has 6 surfaces, and so you can take the electric field on one surface times the electric field through that surface and go through each surface. But if the electric field is changing, you're going to have to do more than just take the full area times the electric field because it's changing. And in that case, you have to replace this with an integral, hence the calculus part. And the reason this is not, I didn't even cover it this year in general physics, only college physics. So Gauss's law says that the integral of the electric field dotted to area, otherwise known as the electric flux, is going to tell me how much charge is enclosed. That we've already done. So Gauss's law says I can tell you how much charge you have inside that box without looking inside. I'll just look at the field lines that enter or exit the box. So here is simple picture ideas to indicate what flux is. If you have the electric field going through a surface like this, it would just be electric field times the area, right? Or excuse me, the red thing should be the area. If it's at an angle, then the amount that is parallel is going to be, if that's my angle theta, actually I meant to make this a straight line, which part of my green vector is parallel to the area? I wrote it with two red pieces. Which of those red sides is parallel to my area? It's actually the horizontal, because this area is a surface that's going like this. And so its area is going like this. Do you understand the geometry?
Wait, I know the surface is a vertical direction. Why is the area?
Okay, so remember, the area is always normal to the surface. So the surface is a physical three-dimensional surface, well, two-dimensional area, like this. So the direction that's normal to that is the direction coming out of it.
Okay.
Oh, I thought you said the direction, like which one goes parallel to it.
I did. Because the area's direction is like this. So the component that's parallel to that is the one that's going like this. It's a confusing topic. It's not a hard one per se. It's a confusing one because of.
So you don't want parallel to the plate. You want parallel to the lines coming off of it.
You want parallel to the normal.
Okay. Okay.
Okay, so the normal is defined as the area.
The normal is defined as the direction of the area.
Okay, I've never heard of like direction of the area before.
Yeah, exactly. That's why I introduced it and went out to the table, because it doesn't seem to make much sense to you until you know this is how we talk about it. So this component is the parallel component. So if my electric field is like this, how do I get this component? Electric field times
cosine
times cosine.
Yeah.
And so that's why this equation up here says E times A times cosine theta, where theta is the angle between the normal to the surface and the electric field. And once again, it's really important to remember it's normal to the surface and electric field, not between the electric field and the surface.
So why is A in there?
Well, remember, the flux is integral of E dot dA. And so this here is doing the non-calculus version. So right, if you have a constant electric field, you don't have to do the integral. You can just multiply. If it's variable, you have to. Now, here's the, I know I scrunched the equation, my mistake. Here's the equation that I've been writing for flux. For a closed surface, the flux is positive if the electric field lines leave the surface and negative if they come in. So if I have a box and the flux is positive for that box, that means I have more electric field coming out than I have going in. Does that make sense? And if I have more flux coming out than going in, what does that tell you about the charge inside the box?
People going in.
If I have more coming out than going in.
The charge is more inside.
The charge is positive inside, because you have more coming out and it comes out of positive. So now we're going to get to how we actually write the equation and then use it. So here is the actual Gauss's law equation.
So why wasn't the cosine theta in the integral?
Because that's part of the dot product. Right, E dot A is E times A times cosine of the angle between E and A. And so here we're going to have, I made a boo-boo. You can't have an integral without a D. I don't know how I forgot that, but I did. So the flux is E dot dA, and the flux enclosed by a closed surface. So it's important that you have a closed surface when you're applying Gauss's law. Up to now, I've just talked about flux, but now it's flux from a closed surface. And do you notice that this integral sign looks different? That circle means for a closed integral. So in this case, because it's dA, it's a closed surface. If it was dL or ds or something like that that indicates a line, then it would be a closed loop, because we're going to use it in both forms. So that's a new integral sign. It doesn't mean anything super tricky. It just means we have to have a closed surface. We can't have any holes in it, no gaps, because we need to calculate the total flux coming out. So finally, charge enclosed is the charge enclosed by our surface we're calculating on. Remember, it's not necessarily a physical surface. It's a calculational surface. We call that a Gaussian surface. That's the surface that we calculate Gauss's law using. And so we come up with that using symmetry to help us. Q enclosed is the charge that's enclosed by that imaginary surface. And then this epsilon 0 is the permittivity of free space. It's a constant, 8.85 times 10 to the minus 12 with whatever units. Yeah.
What is the K? What constant is that?
Okay, so K is the one that's 8.987.
I don't know if we tried to do K or
whatever. I forget the next digit. Let me just put 8.988. I think it's 8.9876 times 10 to the 9th Newton meters squared per Coulomb squared. That's what K is. K is based on epsilon 0. K is equal to 4 pi over epsilon 0. Epsilon 0 is the true constant there. And K we use to simplify our lives when we're using Coulomb's law. So, using this, how to solve problems with electric field. Now, first of all, problem 1, hopefully you have that done by now. I believe I did both parts in class last week, or 2 weeks ago, last time we met. So hopefully you have problem 1 done. Problem 1, the idea you're going to use is Coulomb's law. Now, the reason you're going to use Coulomb's law rather than Gauss's law, obviously at that point you didn't know Gauss's law, so it was the only one you knew. But there's another reason. If you have a good exploitable symmetry, Coulomb's law is harder than Gauss's law usually. But if you don't have a good exploitable symmetry, because you're doing the integral of a dot product, Gauss's law usually comes out harder. So you want to use the easiest method. So each one of those problems has a specific method that you should use. If it has a nice exploitable symmetry, you should use Gauss's law to find electric field. If it doesn't have a nice exploitable symmetry, then you're probably going to use Coulomb's law. But that then begs the question, what's a nice exploitable symmetry? You see I've got it up there in red. What is a nice exploitable symmetry for us to use? A nice exploitable symmetry is going to be a symmetry that allows us to, and I'll just scroll up and right here. Exploitable symmetry. All surfaces have a electric field is perpendicular to the area, so E dot dA is 0. That's one option. Or B, So you see what I did there? The flux is integral of E dot dA. I said for each surface, and then I did it as if it was for the whole thing. If the angle between E and A is constant, I suppose I should have put E dA cosine theta, where theta is a constant angle. That's just a little more general. Usually it's going to be parallel, not 45 degrees everywhere. So if we have one of those two situations, the electric field is perpendicular to the area, or the electric field is constant and a constant angle to the area, that's going to make our integrals easy. There is one third option. The third option is if the electric field equals 0 at surface. So if you have those situations, if you can make a shape that's going to fit those, then Gauss's law is going to be easier. If not, then Gauss's law is probably not easier and will generally go toward Coulomb's law to how to solve it. So with those in mind, let's look at symmetries. What type of exploitable symmetry does a sphere have? That is, what shape could you use for a surface to match one of those three rules I gave you? If I have a spherical charge distribution, so I have a spherical symmetry for my charge distribution, then what kind of shape can I use that will make it so the electric field is constant on the surface and the angle between the electric field and the surface is constant? Well, three-dimensional, so a sphere. So if you have a spherical charge distribution and you use a spherical shell, if it's a spherical charge distribution, then it doesn't matter what angle you are around it, it's always going to look the same, right? If you have one of these little BBs, if the BB is truly spherical, then it doesn't matter what orientation I hold it looks exactly the same, right? That's what spherical symmetry means. So it simply doesn't matter what the angle is and what direction the electric field line is going to go from a spherical charge distribution. It's going radially outward. What direction is the area for a sphere? Radially outward. And so the angle between the electric field and the area is 0 degrees if you have a spherical distribution and you use a spherical shape. So calculation.
We're just talking about an electric field coming out of this object?
Yes.
Okay.
We're going to calculate the electric field. And so we're using our ideas, our knowledge about symmetry to simplify our work. So which one here then is the answer? What type of exploitable symmetry does a sphere have? Spherical. Right, and you probably would have answered that without any thought, but I wanted to make sure you understand the why of it. So if you have a spherical charge distribution, if the angle doesn't matter, it's just the radius that determines the charge distribution, then you should use a spherical shape in Gauss's law. By the way, when you do your integrals, you're going to want to use spherical coordinates then. You guys haven't got spherical coordinates yet, have you?
Briefly.
Yeah.
Briefly?
Yeah, we had a little bit.
Oh, it was on the test?
Yeah.
All right. So, a first question. What is the flux through a sphere of radius 5 centimeters that has a point charge of Q equals -2 microcoulombs at its center? There are two ways. The electric field is known from Coulomb's law and can be used to find the flux, or we can use Gauss's law. So, how do you find the flux? Right? So using Coulomb's law, what's the electric field at some distance r from a charge q? K times q divided by r squared. The voltage in the electric field, one has r, one has r squared down there, so it can be confusing. And then we have r hat for the direction. So that's our electric field. What is the area? Actually, I'm not even going to do dA. We don't really need to use spherical coordinates because we don't have to do the integral. What direction is dA? It's dA in the r hat direction. dA is the magnitude, r hat is the direction because it's radial outward. If we have a sphere that's concentric, it does need to be concentric with your charge distribution. You can't have the charge is centered on my fist here and do a sphere that's centered over here, right? That symmetry doesn't work out for you. So dA is equal to, dA vector is equal to dA scalar times r hat. And so that means I do integral of kq over r squared r hat dot dA r hat. What's r hat times or dotted with r hat? What does the hat mean? With a magnitude of 1. So r hat dot r hat means 1 in this direction times the parallel part of 1 in the same direction. What's 1 times 1? Clearly 1. I know you guys know that one. And if they're in the same direction, r hat times r hat just gives you 1. So this is...
So could you have 4r hat? Is that possible?
Could I have what?
Like 4r hat, for instance?
Yes, the r hat is 1 and 4 would be a magnitude to go with it. So I have this integral of kq over r squared dA. And you might say, well, wait a minute now. My dA, I have a variable there that I'm integrating, and then I have r, another variable. But we are working at a specific radius. R is not a variable here. We're saying at what distance. So it said there r is 5 centimeters. So r is a constant. And so the only thing that's not a constant is dA. What's the integral of dA? By definition, A. And that's all the integration we're going to be doing today, my friend. Now, there's one last step. What is A? If I have a sphere, what is A? The surface area of a sphere. It's 4 pi r squared. The volume is 4/3 pi r cubed. And people get those confused because you rarely talk about this area of a sphere, and you often talk about the volume of a sphere. So putting it all together, I have my flux is equal to kq over r squared times 4 pi r squared. It's kq times 4 pi. Hopefully I made no mistakes, right? So that's one way of calculating the flux. And in your problems, you're going to calculate the flux both ways and set them equal to each other. So you have to be able to do both because you're going to do both in your problems. So that was the direct calculation of flux. The second method is to use Gauss's law. Gauss's law says that the flux is equal to the charge enclosed over epsilon 0. Well, the charge enclosed is the entire Q. And so I have two equations for the flux, Q over epsilon 0 and KQ times 4 pi. And right about now, you're all, wait, but shouldn't they be the same? Well, remember, K is equal to 1 over 4 pi epsilon 0. I wrote it wrong. I wrote it wrong here. Or no, I didn't. Yeah, I did. I wrote it wrong there because I wasn't thinking. So K is 1 over 4 pi epsilon 0, which means that KQ 4 pi is equal to 1 over 4 pi epsilon 0 times Q 4 pi. Cancel those 4 pi's, and that's equal to Q over epsilon 0. So for this simple problem, like that was a simple problem. We could run it from both sides. We had everything in duplicate, really. But that shows us what we have with Gauss's law.
So is Gauss's law only used to do pretty straightforward things like that?
By you and me, yes. It can be used. You can completely get rid of Coulomb's law and just use Gauss's law for everything. But it makes your life harder in some cases. So we only use Gauss's law when life is going to be simpler for us. So Gauss's law is usually used to find the electric field. That's how you're using it in your homework. And so let's make sure that we can do some problems with Gauss's law. And I'm going to skip over. This is just saying how charge can be distributed. We already saw that when we did Coulomb's law. It can be on a surface, it can be in a volume, or it can be on a line. What type of exploitable symmetry does an infinitely long straight wire have? This is not like your homework problem 1. This is infinitely long.
Yeah, I think I'd say planar, but I don't know why.
Okay, let's remember the things we're looking for. We want either of the following 3: electric field, or electric field is perpendicular to dA. So if I have a wire, what direction should the electric field lines point from an infinitely long wire?
Wait, from the electric field?
Yeah, let's take Nathan's meter stick here. Let's say the wire is like this, but it's infinite. It goes forever up and down. They're going to have to point out radially. They can't point up or down. You have just as much charge below no matter where you are. So they have to point outward. So what kind of surface would match the top one there, where electric field is constant on a surface and the angle between the electric field and dA is constant? Okay, a cylinder. Because a cylinder out here is going to, at all places, have the electric field is parallel to the area. And if it's a constant radius from this, the electric field strength is going to have to be the same, because rotating this isn't going to make any difference based on our symmetry. So an infinite cylinder would work. Well, infinite cylinders are kind of hard for us to deal with. So what we do is we make a Gaussian surface that's a cylinder of arbitrary height h. Well, if I have a cylinder of arbitrary height h, then it has a top and a bottom to it. So we have to look at what the flux is going to be for the top and bottom. So what direction is the electric field going to be at the top of my cylinder? The electric field has to be pointing out radially. So the electric field is going like this. What direction is the area at the top? That's upward. What's the angle between those two? 9 degrees. The electric field is clearly going to change as you move in and out on the top, but it's always going to be perpendicular. So we're going to have the blue condition there for the top, and of course by symmetry the bottom. And we're going to have the red condition for the sides. So the cylinder is going to allow us to solve for the electric field at any location from a charged wire. So let's say we have, using like your homework problem, except your homework problem has a semi-infinite wire. It only goes infinitely in one direction and you're on the other side. In that case, your symmetry is broken. And so it would be very difficult to use Gauss's law on your homework problem because the symmetry is broken. But for this, we can make the wire that's infinite, has charge per unit length, and so I'm going to choose some little box here that has dq is equal to lambda dz. There's my z direction. Well, there's my x direction. There's my z direction, okay? So I'm going to have dq is equal to lambda dz. And I write this. I'm not going to do any integral. You understand that, right? We're using our symmetry arguments to make our integrals trivial. Trace is kind of calculus. So I have that dq is equal to lambda dz, but then I'm going to make my Gaussian surface here, which is not a real existing surface. It's an imaginary one for calculation. And it has some height h and some radius r. And then I start my calculation. I say the charge enclosed is equal to lambda times height. I don't even need to use that dq as lambda dz. It has a certain charge per unit length of lambda. So the total charge enclosed is the charge per length times the height. So I've got my q enclosed. Boom, done. Then I go to the fluxes on the different surfaces. So I'll have the flux on the top. And the flux from the top is equal to 0 because the electric field is perpendicular to the, I should have drawn here. It's always best to draw the direction of your electric field. What was that?
Okay, it's still pointing that way on the top.
Yeah, the electric field is radial everywhere, whereas here's the direction of dA top, and then here's the direction of dA on the side, right? And by symmetry, I'm not going to draw the bottom. I'm just going to go ahead and say the flux in the bottom is the same as the flux in the top. And so finally, I have the flux in the side. I can't have the circle on that integral because it wasn't a closed surface. It was just the top. That's not a closed surface. Likewise here. Okay, so because the electric field and the area on the sides were the same direction, so going from the first integral to the second integral, I did two things. I said they're the same direction, so the dot product just became E dot dA, or E times dA. And then E on the side is constant, so I brought the E outside of the integral. And then, of course, by definition, the integral of dA is just A, so the flux on the sides is E side times A side. What's the area for the side of a cylinder? And I mean, nobody knows this one offhand. You have to take a circle. If you take a cylinder, if you were to split it, you would divide it out to a rectangle, right? And the height would be h. And what would the base be? What do we call the thing that the base would be if we split the cylinder and flattened it out? Well, for a circle, the length going around is the circumference. So the area for the side of the cylinder is the circumference times the height. So a side is equal to circumference 2 pi times radius times the height. Right, that's the circumference times the height. And so now I can say the total flux is equal to 2 pi RH. And then according to, and I'm going to change color for this, according to Gauss's law, the total flux should also equal the charge enclosed over epsilon 0. And so I look at that charge enclosed, we had it right here, lambda times height over epsilon 0. And now I can solve, whoops, what did Richard Webb forget? I only put the area here. I forgot to put the E. Right, the flux is electric field times area of the side, not just area of the side. So now we solve this for electric field. Remember I said that's what we usually use Gauss's law for, to solve for that electric field. So at this point, I have a pretty simple equation. If I want to solve for electric field, I just divide both sides by 2 pi RH, so that stuff cancels. Notice my H's cancel. It's really important that the H's cancel. Remember, H was arbitrary. I just said we choose some arbitrary height H. If the H didn't cancel, then I would have a problem. My method would be a full fail. And so what we're left with is the electric field due to an infinitely long wire is lambda over 2 pi epsilon 0 r. Notice from a wire, the electric field drops off as 1 over r. How did the electric field drop off for a sphere? We learned that from Coulomb's law, and we used it just a few minutes ago. For a sphere, it was kq divided by r squared. So for a spherical distribution, it was 1 over r squared. For a line distribution, it's 1 over r. What's the difference? Well, the difference is with the spherical distribution, we had the electric field radiating outward and the lines getting farther apart in all directions. For the cylindrical distribution, for the linear charge, the electric fields are remaining all horizontal, so they're only spreading out in one direction, not two directions. So that's why it's 1 over r squared versus 1 over r. Any questions about this example of using a straight wire? Okay? I just did this. Isn't that what this? Oh, I did it on the question slide instead of the one that actually says do it. And so here's pictures to illustrate what I've been doing, just, better pictures than I draw manually. Here's a question that you already know the answer to. Which statement is true about the electric field inside of a conductor? So if I have a conductor like a solid piece of iron, what's the electric field inside of that solid piece of iron? It's zero. It's zero because if it wasn't zero, then conduction electrons on the inside of the conductor would have a net force on them. And that net force would make them move. And they would redistribute themselves until the net force was zero. And so the charge is going to move around until you make the electric field inside of a conductor zero. So that allows us to do some really cool kinds of problems, again, using Gauss's law. So here, a solid conducting sphere that carries a total charge of minus 16 microcoulombs is placed at the center of a hollow conducting spherical shell that carries a total charge of plus 8 microcoulombs. The conductors are in electrostatic equilibrium. That means we don't have charge moving around. Determine the charge in the outer and inner surface of the shell and sketch the field diagram. We could do this lots of different ways, but Gauss's law is best. So here's pictures to illustrate. So we have, now that illustrates the answer, but I want to see the picture. So we have minus 16 microcoulombs at the center. QC equals minus 16 microcoulombs. And then we have plus 8 microcoulombs on the outer. Q shell equals 8 microcoulombs. Right? So there's our picture. Now, I have a couple different things here, and I wanted to do this using Gauss's law. So using Gauss's law, if I take a Gaussian surface that's inside the center sphere, what do you know about the electric field in a conductor? It's zero. So that means the total flux on any shape I make within the conductor is going to be zero, which according to Gauss's law tells me how much charge is enclosed by any shape I make inside the conductor. What's the charge enclosed by any shape I make inside the conductor? I'll rewrite Gauss's law just to make sure we're clear on this. The flux is equal to charge enclosed over epsilon 0. So if the flux for any shape inside the conductor is 0, then how much charge is enclosed for that shape inside of the conductor? Zero. So that means that I must have a net charge of 0 everywhere inside of this inner sphere. So where is this minus 16 microcoulombs going to be if anywhere inside the sphere it's 0 charge? Has to be on the surface. So I instantly can say this negative charge is spread out. See, I'm still on red, that works. All along the surface. So those are supposed to be minus signs for electrons all along the surface. Now, let's say that I make a Gaussian surface that's here in between the inner and outer shell. According to Gauss's law, what is going to make the electric field or the electric flux for that surface? Gauss's law says that the flux is equal to what? Or what is the flux equal to? It's a simple question. It's not a hard one. I don't want people to be scared to answer. According to Gauss's law, the charge enclosed is equal, or the flux is equal to the charge enclosed over epsilon 0. So what charge is the flux dependent on?
What is the flux?
Yeah. Which charge though? The charge at the center, the charge that's enclosed. It doesn't care about the charge outside unless it breaks the symmetry. If it breaks the symmetry, the charge outside is going to make us have a hard calculation. It won't change the flux. It'll make you have a hard calculation if this charge outside is not symmetrical. So the law still holds if it's not symmetrical, it's just going to be hard to use. So here, our symmetry is held because everything's spherical. And so I can say, okay, for this here, I'm going to have, and so I'm going to call this E in. The flux inside is going to be equal to all the same work we've done before, integral E dot dA. But on the inside, the electric field is going in, the area is going out radially. So those are parallel to each other, anti-parallel. And the electric field is constant on that surface. And so when I do this integral, it just comes to be the electric field times the area, or equal to electric field, I should have put in, times 4 pi r squared. And according to Gauss's law, that should equal the charge enclosed, which is QC here, divided by epsilon 0. And so that tells me the electric field inside is equal to QC over 4 pi epsilon 0 r squared, which is exactly the same as what we've seen with Coulomb's law. En is equal to KQ over r squared, since K is 1 over 4 pi epsilon 0. So the electric field between the shell and the core is the same as it would have been if the shell didn't exist. It only depended on the charge at the core. Now let's go out further. Let's say that I want to check what the electric field is on this dashed line. What's the electric field at that radius? It's 0, right. It's 0 because my surface is completely inside the conductor where the electric field is 0. So if the electric field, field is 0, then the electric flux is 0. So how much charge is enclosed by that black dashed line?
Will be the charge inside, not on the inside of the conductor, but within the shell.
Well, by definition, it's the charge within the black dashed line. And since we know the charge is only on the surface of the conductor, it's going to be the charge on the inner surface of the shell plus the charge at the center. And it's going to be 0 because the flux is 0. According to Gauss's law, if the flux is 0, the charge enclosed is 0. So how much charge must I have on the interior of this, shell? There's minus 16 microcoulombs at the center, and then you have 0 charge enclosed by this black thing. So how much charge must be on the interior of the shell? Actually, it's got to be plus 16, so it adds to 0. So I have plus 16 microcoulombs on this surface. Well, now if I come out and I make my shell here, well, let's do the next thing automatically. It's simple. If the shell has plus 8 microcoulombs and there's plus 16 on the inner surface, how much is on the outer surface? Minus 8. So we have minus 8 microcoulombs on the outer surface. And then if we take some surface out here, the total charge enclosed is going to be, since the plus 16 and minus 16 added up to 0, we just take that minus 8 on the outer portion, and we're going to have the electric field outside is as if you had a charge of minus 8 microcoulombs at the center. So we can construct the entire electric field picture using Gauss's law. We can determine how much charge is on each surface. So here's pictures showing what it actually looks like for the solution. Now, that is the end of my lecture, and we're out of time. You're not going to be able to do all of the problems still. Please come to me for help, and then next class period I will go over the additional problems that you don't have the information to do are the one with the atmosphere, looking at the electric field in the atmosphere. And, well, the dipole one you can do, it's just using Coulomb's law. So you can do the dipole one. So basically you cannot do the one with the atmosphere problem. You should be able to do the others, but they're going to be hard. So come talk to me, ask me questions, I will help you. And then next class period, I will make sure I go over the one that you can't do at this time, the one with the atmosphere, and answer any questions that remain. Yeah.
How will that impact reviewing for the test?
Well, okay, that's a good question. I'll keep the recording going here. So for the test, you are going to have a problem that requires you to use either Gauss's law or Coulomb's law in the fashion of what's in this homework. So this homework is helping you prepare. Now, your problem on the test is not going to be as difficult as any of these problems. Right? These are not simple. That's why I didn't have, here it is, get it done tomorrow type thing. But these will be helping you for the test. All right. I will see most of you